All right, 5.2 has too long of a title for it to actually be used as a title for a file in my computer. Isn't that crazy? What's the actual title? It's not even on your paper. I didn't even write it as a title this section. It says something about graphing polar coordinates and DeMoivre's theorem or something like that. Yeah, DeMoivre's theorem is what we're just going to call this because that's where we're going to end up at the end of all of this, but we do have the graphing part at the beginning to contend with. So this is DeMoivre's theorem. DeMoivre's the mathematician, worked with the complex number system, and so we're going to take a look at some of his work in this section today. The material in this section is used in physics courses. It is used in later calculus courses, so this is a build upon kind of thing. It's kind of like the other day I was working in one of my classes and we were doing something in Calc 2 that hinged upon something from Algebra 2 in high school. And I had a student that said that. And they were like, this is Algebra 2 stuff. And I was like, yes, it is. And that's why we teach it in Algebra 2 is because for some students, if you get far enough along, it's going to be utilized in a later course. That's how math is. It builds on itself. So this is one of those building sections. All right, for starters, we're going to take a look at how we graph in the complex number system. And it's actually very straightforward in terms of the initial picture of it. And so in the real number system, we normally have an x and a y plane, right? X and y line, right? An x-axis, a y-axis, and they look like this. Well, we have two axes just like this in the real and imaginary, or in the complex number system as well. They are the real axis and the imaginary axis. So let's label them as such. This is my real axis. And this is my imaginary axis. And this word imaginary, I didn't mention it last time, but this imaginary is not like an imaginary friend. Okay, it doesn't mean it doesn't exist. It's a terrible name, but it's one of those things that sometimes names stick, even when they're bad. Okay, so we use this word imaginary to mean something very different in sort of our typical language. But these are just called imaginary numbers, complex numbers. So if we have a number, a plus bi, and just for the sake of my drawing, I'm going to say that a and b are both positive, okay? Because it's going to make sense. Then what happens is I move on the real axis a units, and I use the imaginary axis and its b units, and this is my point a plus bi. So the real axis, this is the positive side, and this is the negative side, just like with the xy coordinate plane. On the imaginary axis, this is the positive axis, and this is the negative axis. Make sense? Okay, so the second thing that we're going to need for our first set of directions is the absolute value of a complex number. So the absolute value of a complex number, z equals a plus bi. So we draw the absolute value signs in, right? Absolute value of a plus bi. It's the square root of a squared plus b squared. Now, we have seen this kind of formula show up several times this semester. Can somebody think of where you see this general formula showing up? Where do we see it showing up?
Pythagorean theorem.
Pythagorean theorem is one of them, definitely, right? A squared plus b squared equals c squared. If you're trying to find c, you take the square root. That's one of them. You've seen it more recently, too. What'd you find? Magnitude of vectors, right? This is magnitude of vectors because you know what we're really finding when we're finding the absolute value of this imaginary number or this complex number is we're finding this length right here. And what does that length look like? A vector. And it looks like the hypotenuse of a right triangle, right? It all goes together. It's all the same stuff. So we see that same formula showing up. This is the square root of a squared plus b squared. I would like to give this another, they use the letter z right here, so I'll call it z for the moment. They will be using later on the letter r, kind of like the radius of a circle r, when they're talking about the distance away. So you'll see them use that interchangeably as well, okay? So this is our our absolute value quantity, a squared plus b squared, and then square root. So we're going to take a look at finding the absolute value and graphing these kinds of numbers. So this first one is z equals 3i. So we are going to graph it first. So if I have my graph, where will z equals 3i be? It'll be on what we would have had the imaginary axis or what we would have previously called the y-axis, right? And how far up will I go? 3. And why am I going up instead of down? Because the 3 is positive. Excellent. So we're going to go in here. We're going to go 1, 2, 3 up. And this is our point that we have here, correct? Now, I don't probably really need to calculate this. How far away is this point back to the origin?
3.
It's 3. Now, from the perspective of the formula, what we actually have here is 0 squared plus 3 squared, because there is no real component, or the real component is 0. So it matches, from the definition as well. But we don't really have to calculate this, because the distance from the origin to my point is very clearly 3, because it's a vertical distance. So if I have an imaginary unit, I can just count how far I am away. If I have a real unit, the same thing is true as well. So if this had said to graph the real number 5, well, we would have moved 5 in the positive direction, right? And the distance back to the origin would be 5. So the absolute value would still be 5. All right, let's take a look at one that's more interesting, though, because it does have a real and an imaginary component. I have -3 minus 4i. So axis, real and imaginary axis. Where will I put -3 minus 4i? Okay, there we go. Left 3. 1, 2, 3, and down 4. 1, 2, 3, and 4. I'm right here for my ordered pair. Or not my ordered pair, my complex number. In quadrant 3, right, if we're thinking about it from the way we've been thinking about these quadrants before. Okay, everybody good with that? That's my graph. Straightforward, plot the point. And then how am I going to find this length? Because that's the absolute value. Yes, I have the square root of the 3 part thing being squared, the 4 part being squared. They are negatives. Those will eliminate themselves. And I think I already did that numbers today. 3 squared is 9. -4 squared is 16. What is 9 plus 16? Yep, it's 25. And the square root of 25 is 5. So the absolute value, or the length back to the origin, is 5. Okay, everybody good? All right, so what we've done so far is looking at complex numbers in what's called the rectangular coordinate system. I have an kind of like an x component and a y component. I have a real component and I have an imaginary component. There is another way to think about our complex number system, and this is in what are called polar coordinates. So the polar form of a complex number, a plus bi, is written in polar form as z equals r times the quantity cosine theta plus I sine theta, where the a value is r cosine theta, the b value is r sine theta. R, this is the same r we talked about as z before, r is the square root of a squared plus b squared. And this angle that's showing up is found by finding tangent of theta equals b over a. There's a name for r and for theta. R is called the modulus. Right? We talked about absolute value before. This is another name for it. It's a modulus. And the angle theta is called the argument. So I want to just quickly graph for you what that ABI business looked like before and give you a perspective of what r and theta are from this graph. So before we had a here, we had b here, we had this point, and it was a plus bi. Shake your head if that looks like a familiar picture. Good deal. And we talked about the fact that this length right here was the absolute value. Yes? In terms of polar coordinates, this is the r, and this is theta. So instead of measuring our x distance and y distance, right, our a distance and our b distance, we measure how far away we are and the angle that we are away from the x-axis. That's what polar coordinates do. And if I drop these in, which I will, check this out. This would be b, right? That's the length of b. And this piece over here would be a. Whoa. A, right? And if you think about this as a triangle from the things you've learned in trig, what's the relationship if you use the opposite side and the adjacent side? It's tangent. So the tangent of this angle theta from this triangle is the opposite, which is B, over the adjacent, which is A, which is exactly that other equation above. And if you look at the other two, we'll look at the value for just, let's do the A one right here. Let's do this one. The same thing's true for this one. If I look at where the R and the A are, and I can compare them, so to speak, these two pieces, the relationship within the triangle here is cosine because this is the adjacent side and this is the hypotenuse. So if I were to write the same sort of formula out here and I wrote down the cosine, of theta, it'd be adjacent, which would be A, over hypotenuse, which would be R. And if I solved this for A by moving the R to the other side, I would find that the R cosine of theta is equal to A. The entire polar coordinate system is built on all the trig you've been doing all semester. It's nothing new. It's just a different application. Okay? So we're thinking about our ordered pair, or in this case, our complex number in a slightly different way, but it works with all the trig that we've done in the same way we've done things before. So let's take a look at an example where we think about these in terms of polar coordinates. So we're going to plot the complex number. That's fine. We've already done it and looked at how to do that. And then we're going to write the complex number in polar form. And it tells us that we can do this with degrees or with radians, so we get to pick. Okay? I'll do it in both ways, so you have both of them written down in case there's a specific one that's asking you for that inside of my math lab later, and it says to do one specifically. Okay, so starting with, we're going to graph. Okay? So where will this -4 be on my graph? On the real axis to the left, 4 units. That's -4. Everybody good with that? Okay, so let's think about this from a geometric, right, from a picture point of view. Okay, so I am a visual person. Like, I think in terms of things a lot more visually than I think of formulas. I can memorize formulas, that's fine, but they don't have a lot of meaning to me. But pictures, to me, give me a lot of information, and I find them easier to use. If that's not how you think, that's fine. I gave you a list of 3 formulas, and you're welcome to use them, okay? But what I want you to see from this in terms of the visual is that we need an R and we need theta. I mean, that's what we need from this picture. The R will be the distance back to the origin. What's my R for this problem? It's 4. My theta will be the angle measure back to the positive axis and the real number axis over here. So what is this angle right here? It's 180. Or if I'm doing it in radians, what is it? Pi. It's 180 or pi. Okay, are we good? So then, what this is telling us is that our, well, let me write it down as it was originally so that you have it here too. Z equals A, and then it was cosine, not A, that was R, sorry. R, cosine of theta plus I sine of theta. This is the form that we're looking to putting it into. This is where the R and the theta are coming from. So for us, we found out our R is 4, and we found out our angle is 180. So if I take the R and I put that in as 4, and I put my angle 180 in, this is what this number would look like in polar coordinates. Okay? Now, if you're like, well, why don't we just simplify the cosine 180 and the sine 180? Well, if we do, we're going to get right back to the fact that this is actually equal to -4. That's turning it back into rectangular, okay? If we write this with radians, it would look like the following. Right? So depending on if we need radians or we need degrees, these are the 2 versions that we would get. Now, again, kind of like with the first example we did, this feels a little bit contrived. It's like, well, yeah, but you're on an axis. It was easy to count back and see that you were 4 away. And that's a valid statement. It really is very straightforward because I am on one of the axes, right? So we're going to do a second example where we're not on the axes to see what happens when we are not on the axes. And then either from the visual or from the formulas, we have to work just a little bit harder, okay? So here's another one now. This one, rectangular form. I can graph this, that's fine, but it's not near as pretty to graph. It just isn't. So let's take a look at what this looks like. So I need to go right one because that's one. That's the one part. What am I going to do to get the I squared of 3? I'm going to go up because that's a positive square root of 3. What is square root of 3 approximately? 1.5-ish, right? Like it's more than 1, it's less than 2. So in terms of the graph itself, it's somewhere in between the two, say something like that. Okay, so we're eyeballing it a little bit. Agreed? Okay. So this is our number 1 plus I squared root 3. R is harder to see on this one, right? It is. The R value that I'm looking for is right here. This is the distance. And the theta value is here. I need the R and I need the theta. Now, you're welcome to go back to formulas. But I'm going to tell you also, this is something you've seen before. So let's look at it from a formula perspective this time, since I did it from a geometric perspective last time. So R is found by doing the square root of each of these individual components squared. So I have 1 squared and square root of 3 squared. So 1 squared is 1. What's square root of 3 squared? 3. 1 plus 3 is 4, and the square root of 4 is 2. So this length right here, I'm going to make it a little bit bigger over here to see it. This length right here is square root 2. Or not square root 2, apologize, 2. And it came from the fact that we had these sides given, give or take, where this is a 1 and this is a square root of 3. Are you with me? That is a triangle that we have dealt with. In fact, you've memorized a unit circle that deals with it as well. Now let's say you still are looking at it, because some of you are, and you're like, I don't know what she's talking about. That's okay. Let's figure out what our angle is based on just the picture without relying on the fact that we've memorized this before, okay? So let's find this. This is the theta we're supposed to be finding right here. This is just my picture that I drew originally, drawn bigger. That's all this is. I should have just drawn it bigger to start with, but I didn't. So if I'm trying to find theta, my formula is that the tangent of theta, right, from my triangle is supposed to be opposite, square root of 3, over adjacent, which is 1. Everybody good so far? So either we need to think unit circle, where do I get tangent square root of 3, which is not super straightforward. If it had a sine or a cosine value, you'd probably be better off. Or grab your calculator. So grab your calculator for me. We'll do it in degrees because radians, if it has any pi's in it, which it will, are not going to come out as a whole number, but degrees will. What is the inverse tangent of square root of 3 in degrees? It's 60. You were close, Giannis. Yeah. You're close. 60 degrees. Okay, now I do want you to pause for a moment because I don't want you to have to figure it out with actually computing. But what is that in radians? Do you remember what that is? It is pi over 3. Yeah. Remember, you can turn it into radians if you want by multiplying it by pi over 180, but it is pi over 3. So we now have the R value, and we have the theta value in two forms, which means we can write this in polar form. So this Z is going to be equal to 2 times the cosine of 60 plus I sine 60. Or if we do it in radians, Z will equal 2 cosine of pi thirds plus I sine of pi thirds. Now, you may be looking at these and saying, okay, fine, you can change it into this other form, but the form that you're changing it into, Dr. Hans, looks terrible. Why would I ever want to do that anyway? That seems so unproductive. Hold tight. We haven't finished 5-2. It will become clear why that's helpful in a moment. Okay? I'll see you guys on Monday.